Hi, my name's Pat Blatt. I'm Dr. Daniel Hallinen's student, and I've been tasked with making some COMSOL problems to integrate with your chemical engineering classes, and I guess some biomedical classes as well. So today, this is kind of a pilot test of the ideas I've had. So I have a step-by-step Word document that you could follow for each of these things. And I'm going to be time stamping specific sections by the skills you'll learn in each tutorial. Today I'm highlighting a very simple example as far as the geometry and the physics involved, but I'm hoping to highlight a number of the most important things you'll be doing in COMSOL, the most fundamental operations. So looking over here to the Word document, which you'll be provided with, basically what COMSOL allows us to do is, as chemical engineers, it's exceptional at allowing us to quickly model heat and mass transfer, which in short is kind of what we do, or at least that's how I describe it to non-chemical engineers. So this problem is a very simple conduction problem at steady state. So it's something you've probably seen before, but we're going to use that simplicity to focus on complexity in COMSOL. By the end of this module and this video, you should know the basics of operating COMSOL, where things are, what they look like, and the CAD system. So the CAD system is just how we physically draw a real-world object and represent its shape and properties in the computer environment. I'll show you how to assign boundary conditions and governing body equations to a control volume, and you'll learn about convection and conduction. So those are the things that are going on. Then lastly, you'll learn about a parametric study and how to do it in COMSOL, which is one of the most valuable things you can do. So there'll be timestamps throughout all of this. So if you're a master at the CAD part of it and you just want to skip it, focus on the parametric study, there'll be timestamps somewhere. So yeah, it's the end of this section. All right, moving on to the next section. We'll be outlining the problem statement to motivate what we're doing. So the premise is you've just begun your new job at a nuclear power plant. A bundle of spent nuclear fuel rods have just been removed from the reactor. While no longer ideal for power generation, these rods still produce dangerous amounts of heat and radiation for decades. Water is employed to handle both of these phenomena, acting as a cooling fluid and a shield from radiation. As your first task as an engineer, you are tasked with overseeing the interim storage for the world's first large-scale thorium fission reactor. The diagram below shows your very important role in this process. So as you can see, there's mining, milling, conversion, and enrichment. So just preparing the nuclear materials to be used in the reactor. And then once they're used in the reactor, they produce a lot of energy, obviously, boiling water. But after a certain amount of time, they're no longer ideal or efficient to be used as a source of energy in a nuclear reactor, but they still give off a lot of heat and energy, and of course radiation. So the way that your power plant is going to deal with this is by submerging them in water. So water will absorb that radiation, and obviously it'll also cool your rods down because of water's extremely high heat capacity. And of course, if it boils, you get a lot of latent heat of vaporization. So your job is to oversee that tank. One day something goes wrong. Your coworker calls you over the walkie-talkie and says, Someone in HR rerouted the water for a team-building water slide. The fuel rod surface is supposed to be kept at 100 degrees Celsius by water, but the surface temperature is climbing. You, as the engineer, know that secondary containment failure is likely to occur immediately if any part of the rod reaches 650 degrees Kelvin. Additionally, the system is also likely to fail if the rod remains above 200 Kelvin for 2 hours. You immediately start pumping water back in to cool the reactor down while monitoring the surface temperature. At what surface temperature reading should you evacuate? Can cooling water prevent gradual failure? So today we're just going to look at the first case of the failure at 650 degrees Kelvin, and we're going to make a pseudo steady state model relating the surface temperature, which you're able to measure through some sort of thermocouple on site, and using a pseudo steady state model to see if the center of the rod will reach 650 degrees Kelvin. And then during recitation, we'll address the second case, the transient case, regarding the 200 degrees Kelvin. So here is the coordinate system we'll be looking at. So obviously, because the rod is a cylinder, cylindrical coordinates make a lot of sense to use. So we have 3 dimensions to consider. We have the z dimension, which is the axial direction of the rod. We have the radial dimension, so how far you are from the center of any cross section. And then you have an angle, which you can call theta, which just tells you where you are along the perimeter. So if you're like 12 o'clock, 6 o'clock, 3 o'clock, that sort of idea. So that's the coordinate system we'll start with, and we'll develop a model using this method. So this might be something closer to what you do in Transport 2, but I hope this is a good example of how to build a model. So I listed out a number of assumptions you can make. So to begin, you quickly make a heat transfer model for the rod. Because you are in a rush and the thermal conductivity of the rod is high, you use a one-dimensional steady-state cylindrical model. Here are the assumptions you can make. The rod's surface temperature is currently at 200 degrees C, so your coworker is calling you over the walkie-talkie, reporting. So your question to answer today is, do you have time to start pumping in water before the center reaches 650 degrees Kelvin? So we have to develop a model that, if we know it's 200 degrees C at the surface, on the perimeter of the rod, what is the interior temperature, and at any of those temperatures does it exceed or match 650 degrees Kelvin. So below I listed some assumptions to make. So this is something you'll become more familiar with in Transport 2, but the idea is we can relate physical realities of the system to parts of equations. So assumption A, the ends of the rod are well insulated, meaning that heat flux in the axial direction is equal to 0. So if I bring back up the coordinate system, if you imagine that both ends are perfectly insulated, there's no temperature gradient in that direction because heat isn't allowed to flow. So if heat can't flow in one direction, there won't be a temperature gradient in that direction. So that's why we can say assumption A, the derivative of temperature with respect to z, or the axial direction, is equal to 0. So that's a pretty big assumption, but it's one we're going to make to quickly solve the problem. And then in future COMSOL models, we will relax that assumption. Our second assumption is that we know the rate at which those radioactive products decay and the resulting heat from that. So that's what H vol is, or H volumetric. So it's the volumetric rate of heat production from this nuclear reaction, and it's 20 to the fourth power watts per meter cubed. So that's going to heat things up. So if we don't cool it down, it's just going to keep heating up and heating up. And then we're given the thermal conductivity. And lastly, we're given the radius of the rod, its density, and its heat capacity. And then boundary conditions. So we're given from our coworker that the surface temperature, so at R, at the radius of 0.5 meters, the temperature is 200 degrees C. And then we can also make this assumption, which is true for cylindrical coordinates. Due to radial symmetry, the first derivative is equal, or at the center of the rod, there's no temperature derivative. So with all this knowledge in mind, we can then write out the conservation equation for cylindrical coordinates. And I just went through and broke down what each term means in a physical sense. So as you can see, on the left, we have the time rate of change of temperature, and all the terms on the right are responsible for that rate of change of temperature. So in purple, we have heat transfer due to conduction, so through the conduction mechanism. And then in green, we have heat transfer due to convection. And then lastly, we have the volumetric rate of heat generated through radiation. So keep in mind, this equation only describes what's happening within the control volume. So bringing back up the cylindrical coordinates, you can see that only inside of the cylinder is this relevant. I bring this up because convection only occurs when a fluid is involved, and our fuel rod is a solid. So this green term goes to 0. There's no convection. We also know that we're assuming a steady state model. So the time rate of change of temperature goes to 0. And then lastly, we're assuming radial symmetry. And by that I mean that the environment at any location on the perimeter of the cylinder is the same. So in other words, the water or the air at 12 o'clock or at 6 o'clock or at 3 o'clock, wherever you're at, is about the same temperature. So the conditions are the same. So we result in just having a one-dimensional problem. So the temperature is a function of just the radius, and you can solve it explicitly. So this model makes a lot of assumptions that we will later see if they pan out. But today I just want you to recreate this in COMSOL. All right, welcome to the next section. So we're gonna build this thing in COMSOL. So the steady state model is pretty simple. We were able to solve it by hand, but once you get it good at COMSOL, you could have done that in a matter of seconds even. So I'm gonna follow the Word document step by step. It's pretty complete, so if you get stuck anywhere, every step is there. So over here, I've just opened COMSOL. All I did was click on the button, and I have version 6.1. So our first two options are Model Wizard and Blank Model. Model Wizard is great when you have a specific problem where you've kind of thought it through all the way to the end. It'll help you fill in some blanks. So in our case, if we click on it, and once again, we'll use 2D geometry. So for instance, the utility of the Model Wizard is if we pick something like heat transfer in solids, we'll kind of know what parameters are needed to solve the problem. So to know, like, we need thermal conductivity, we need density, we need heat capacities. And just having those boxes there ready to fill in can save a little bit of time. But you can access the physics at any point. So for this very simple model, and like I said, we'll build on it to in recitation to discuss the case of trying to cool it down with cooling water. But just for today, let's just focus on something simple and use that to get exposed to some of the most common COMSOL functions. So I'm going to do heat transfer in solids, and of course you can go over here and read about what's going on. So yeah, Fourier's law is the important thing, and we discussed the significance of that a little bit earlier in the document and in the video. So I'm going to double click it until it comes down into the study window and then hit study. So we can do stationary or time dependent. So for now, I'm going to do stationary, and recitation we'll do time dependent. Then if you're unsure about anything, it'll come up with a nice helpful tooltip. Cool. So it always opens like this with the geometry tab. And this geometry window is just us labeling the whole thing we're making. So if it's a big construct, it could represent the entire thing. So it could represent an entire bike. Or you could break apart and have a couple of these large geometry windows. So you could have the wheels on the bike and the bike handles. So at this parent level, you just want to describe one thing that you're going to be studying that has one governing body equation kind of dictating it and what we're studying. So I'm on page 9 of the tutorial. So I've confirmed that my model builder window appears as it does here. So that just means we click the right buttons. So now I'm moving on to page 10. Step number 1, select the geometry 1 option. So we can change the length unit, and that just gives a default length that COMSOL's going to kind of expect. So if we do angstroms, now the grid is now in angstrom, so our obviously our circle would look huge, so it's not great to use. We could scale out, but it's going to default to zooming in way more than we need. So we're just kind of telling it baseline. Most of our dimensions are roughly on the order of a meter, plus or minus a few orders of magnitude. Just making sure I didn't call this anything specific. So I'm just going to name this fuel rod geometry tree. So theoretically, the fuel rod had more than one part. So it was a fuel rod and it had a fin, heat exchange fin on it. There would be those two things underneath this one part. So I'm representing potentially multiple parts under one geometry tree. And then you can hit build all and it returns back to the scaling of meters. So what's next? So yeah, our problem is a circle. So you go up to the geometry tab. These CAD tools are somewhat limited. So personally, what I would do if I was doing something really complicated is I'd probably use SolidWorks and then import it into this. But for, I think, a lot of the undergraduate level work, you can kind of form good enough approximations by adding and subtracting these shapes. So we'll start with the circle. And I'll have a tutorial in the final version of this video. I'll have a tutorial or something that will connect you to a tutorial about adding and subtracting shapes to make bigger ones. So I've selected circle and then it comes down here. And as you can see, the circle is under the parent tree of the fuel rod geometry. So if there's other parts to the fuel rod, we would also keep them under that tree. So cool. I'm on step 4 on page 10, and I called it fuel rod, I guess. So you'll notice I inputted a variable r. In COMSOL, we never defined r, so it doesn't know what I'm talking about. So just like MATLAB or any coding language, you first have to define your variables before you implement them, or they have to be on the left side of an equal sign before they're on the right. So the parameters window is how we achieve that. I listed out what to put in. So I'll put in 1 and then load the rest from file, and I'll provide you with the file to save you some time. But just to use this as an example, the expression is the unit we want, and then in square brackets we put the SI standard unit. So what I mean by that is like a meter is specifically lowercase m. So like the cases matter, and if you're unsure, just look up an SI standard abbreviations, but you should have seen most of them. But fundamentally, most of the time, there's been a few exceptions, but we could input the radius in a different, or we can input dimensions in, we can input parameters in different units than our geometry tree's base unit. So say I wanted to do 50 centimeters instead for radius, it's the same thing. It'll do the conversion right there. So that's what it's reading in. So that's another thing the geometry unit does, is it tells us what, it tells COMSOL what to convert these into as a baseline. And then of course it's good to label everything we do in case we come back sometime in the future. So a useful thing you can do if you're working or collaborating with somebody else, especially if they don't know COMSOL that well, is you can save your parameters to a file. So we can call it whatever you want to call it. And what that'll do is they can reopen the file, and it will it'll repopulate it. So I think I'll put on the screen now what that text file looks like. I'm afraid that my screen sharing is gonna mess up if I do that. So I'm putting it up now. Editing magic. Okay, so that's what it would look like. So I've gone through and made a file that you can load in, but try one to start. And once again, the SI units are here. So I always use the base units, so units derived from kilograms, meters, seconds, and Kelvin, and that just makes unit conversions simple. And then I just want to note here that there's some variables that COMSOL uses, so you can't use them specifically, and one of them is CP, so I had to use CP1, but the text will just turn yellow if it's a reserved variable, so it'll be pretty clear. But I just wanted to point that out. So now we've put in all our parameters, so as we go on we can use the names. I can't point, but yeah, we have all those established. So then we are through question 6, or part 6 on page 10. So now we've defined R, and we can build the object. And then of course, if for some reason we wanted to change R, oh, I guess it was wrong in that little file. So if we change R, and then we just hit build all again, every time we run the simulation, it rechecks the parameters. So just keep that in mind. So next step, just make sure that it looks like the picture provided in figure 3 on page 11, which it does in my case. All right, the next thing we have to do is tell COMSOL the material properties of our rod. So we've already put parameters in for the we've already put parameters in for each of these values, so we can reference them as variables. So what we do is we go to materials, and then we right click and we do a blank material. It's a blank material because this is something that I've made up for the problem, so obviously COMSOL doesn't have the data. But you could browse materials. If you click on this, your material browser comes up and you can look at all these built-in things. It's not super exhaustive, but I found there's enough that you can approximate things. So, you know, even if you don't have the exact metal you want, you can get a metal that is pretty comparable, and then you can go in and change one of the parameters. So for instance, if we wanted copper and we really cared about its density, but we thought the other parameters were, you know, relatively close, we could just come in here and change it to copper, or change the density of copper, and then it'll work. So I've done that for like quick approximations in the past, but we don't need copper. So right click, blank material. Like I said, the value of the model wizard is it kind of knows what it's going to have to look for. So down here in the material contents, it brings up what it needs to solve a steady state conduction problem. So it needs K, needs density, and it needs CP1. So if I input a variable I haven't defined, weird. If I input a variable that I haven't defined, it usually turns yellow. Let's see what's going on with that. CP1, joules per kilograms per Kelvin. Okay, so just bear that in mind. If anything turns yellow, it usually means it's an incompatible unit system. So like if we put in time where it's expecting temperature, it might turn yellow, or if it's an undefined parameter, but we've defined our material. And then of course we want to click on the circle. So you'll see over here in selection, it'll toggle on and off, so make sure it's here. And it's on the domain level. So theoretically you could have like something on the boundary, like we could have a copper boundary for whatever reason. So you can have a boundary material, but in this case, we just want the whole thing to be our custom fuel rod. And then I will name this fuel rod material properties. All right, cool. So so far we've put in our parameters, we've defined our material properties. Now we need to define the governing boundary equations and the boundary conditions. So it's already done a lot of the work for us. So it's saying this domain is a solid, so it can't flow, so only conduction's going on is what it's saying. And then we can look in to see what that means as far as an equation. And this is just the heat conservation equation for a solid. It's even more extensive than the one I showed you, but a lot of the terms go away. But it's just good to know what we're using in case somebody asks you. The initial value, because it's a steady state of problem, it's just like an initial guess. So it doesn't really matter, but I guess in principle you should know that the farther you are away from the steady state value, it'll take slightly longer for the solution to converge. So it's a good idea to not pick something crazy. So I wouldn't put in like 1,000,000 Kelvin. I'd look at the problem and I'd say, you know, your coworker said that the surface temperature was this. So I'm going to make an initial guess of T-surf as throughout. So that's the initial temperature and the full domain. I'll show you in another video how to do a more complicated profile. And then in physics, now we need to add a couple things. So we have the boundary condition is this. So it's a temperature boundary condition. So we're just saying at this point, the temperature is this for all time. And of course, that is T-surf. It's user-defined, and then, like I said, the equation's always there. Temperature is always equal to that temperature T0, and T0 is here. So we've done that, and then of course the last thing we have to do is add a heat source, so the nuclear decay, and that's just HV. And then I think our study should be good to go. Cool, and then I'm just gonna check with figure 5 on page 13. It looks the same to me. So our initial question was, based on what our coworker tells us, the surface temperature is 200 degrees Celsius, and we have to evacuate if the center is at 650 Kelvin. Well, it looks like we still have a little time to cool it down, and that's what we'll do in the next part. But now I'm just gonna give you some more ways you could have looked at this problem. So I'm gonna take a break here. This was just basic model building, and now I'm gonna move on to derived values and a parametric study. All right, see you there. All right, everybody, so I'm picking up with our model. So just to recap, in case you just skipped here, we made a really simple steady state model for conduction in a circle. So really, it's a one-dimensional problem, as we found out when we broke the problem down with our assumptions. And just to give you a page reference where we did that, that's on page 8 of the handout. So you'll notice the only independent variable is R. So really, the best and most efficient way to express our results would be in a one-dimensional plot. However, COMSOL, and the way we set it up, I guess more specifically, is giving us a two-dimensional plot, which is both gives us more information than we need because of the angular symmetry. And also we can't really pick out numbers precisely. So you can see over here, yeah, it's somewhere above 505, probably not too much above, but if you wanted to report that exact value, you'd want to be able to do that. So first, I'm going to give you a method to determine the maximum or average or minimum of any dependent variable at a location in a geometry, and these are called derived values. So they're derived from the model. So the model runs, and COMSOL has all this information, and we just need to use derived values to access them. So I'm on page 14 of the handout, and I'll be following that procedure. So to begin, really what we want to know in this problem is the maximum temperature, because we know if we reach 650 degrees Kelvin, the system's going to fail. So in order to access a derived value, I right-click on derived values, and then it comes up with all of these different operations. So the one that I found is the most valuable, or the ones I found most valuable in my time, are these guys. So we can get the average temperature, the integration, maximum, minimum. And then lastly, we could measure a dimension on the surface, which I'll briefly show you. But in this case, what we care about is the maximum temperature. So volume, of course, corresponds to a three-dimensional problem. Surface corresponds to 2D, and a one-dimensional problem, we would use a line. So our shape is two-dimensional, so I'm going to choose surface maximum. And then I just need to click here and to make sure I've selected what I want to, which I have. The data set we're referencing is study 1, and you'll look down here, that's our stationary study, so it's good to confirm that. And the expression we're going to get out is temperature. So in principle, if we were to do a problem with two dependent variables, we could have, which we will do in the next exercise, we could access either one of those. So we could do like time and temperature or concentration. So any dependent variable we can access in principle. So we've clicked on it. The expression is temperature. I don't think there's anything I want to show you there. So what this will do is it will evaluate. It'll just look through the surface and tell you what that maximum temperature is. So once you become more familiar with COMSOL, if you imagine you were in the situation where it was urgent, you could actually answer the question, what is the temperature at the center of the rod, really quickly. And that's how I would do it. So if you want to, you can go through and do all sorts of other ones. So you could do average, minimum, and all of that. But it's very straightforward. So we'll just stop with that. And then, so that's the basics of derived values, and we'll move on to parametric studies in the next section. All right, welcome to this section where we'll be talking about parametric studies. So a parametric study is when you just take one variable and you change it, usually in a linear way, but you just try out a ton of different values for that variable, and you see how the system behaves. So this is a good way to do an optimization problem, so to find the best value of that parameter to get the system response you want. Or it can just be used to give you like a general idea of the relationships between things. So if I raise the temperature here, how does that affect some other phenomenon over there? So in this case, I'm thinking about our safety limit of 650 degrees Kelvin at the core of the rod. So the question I'm trying to answer is, originally our coworker told us that the temperature was 200 degrees C, and we found that resulted in a core temperature of less than 650 Kelvin. So the question I would like to answer with this exercise is, what temperature, if he had told us what temperature would the core temperature have been 650 Kelvin, and we would have had to evacuate. So what is like the maximum the surface temperature could ever be without that core failure happening? So a parametric study where we alter the surface temperature is the best way to achieve that, or is a way to achieve that. So I'm going to work through page 15 and show you how to do that. So first, for a parametric study, we need a way to measure the response of our variables to the parameter being altered. So in the definitions tab, one of the most useful things is probes, because they allow us to do that. So a domain probe will consider information in the entire shape. Boundary probes will consider obviously the boundaries. And then a point probe behaves just like a real-world thermocouple. But in essence, they're all just measurement devices, and they kind of mimic the things you might use in your process control labs. But really, what we're doing is COMSOL is creating all this information, all these numbers, but it doesn't report it because it would be overwhelming. And these probes allow us to say that we want a specific piece of information. So in this case, we want to know the hottest temperature in the domain. So I'm going to select a domain probe. So I think I gave it a specific name on page 15. Yeah, I named it core temperature. So the domain probe will look through all the temperatures in the circle and look for the maximum if I change the type to maximum. So of course we know that the maximum temperature is going to be at the core. So this probe will now report the core temperature for a given parametric run. So our only dependent variable is temperature, but in principle you can do this with any dependent variable you want to measure. So it's just a way of telling COMSOL, hey, I want this specific piece of information. That's why we use probes. So yeah, we've given a way for, or we've accessed that information so we can hit update results and it will give us the maximum temperature. So that's really the most precise way to quickly answer the problem question, or the question in the problem, is to use a derived value or to use a probe. So yeah, so that's how we use probes, and then probes are important because they're required for parametric studies. All right, so we're gonna do a surface temperature sweep. So we're going to change the surface temperature to see what is the highest surface temperature that could exist that would still be below that 650 Kelvin safety limit. All right, so the parameter we're altering is the surface temperature, so Tsurf. And then I'll just briefly talk about the sweep type. So all combinations and specified combinations behave the same way if you have a single parameter. But in the case of all combinations, if we had two parameters, we would do kind of a factorial experiment. So if you imagine we had two surface temperatures and two, say we wanted to measure rod radiuses, we would have a total of 4 experiments because we would need to do 2 factorial. So that would take it would take a relatively large amount of time. However, specified combinations, it will take the first temperature or surface temperature we put in the list, and it will only run it with the first radius in the list. So that way you would only have 2 runs in that case. And maybe in the final version of this presentation, I'll add some nice graphics to make that clear. But for our case, we're only varying one parameter, so we can use either. So changing the surface temperature. So I go down here to range. There's a COMSOL kind of syntax you could use, but I like the range. So I want to sweep from, what did I say? 200 to 650. And I'm going to take a step size of 2 Celsius. So I'm going to go 200, 202, 204, all the way up to 650. And I'll add it. So that just filled this in, but obviously you could have typed it. And then by clicking plot here, as we run through the experiment, or run through the different values of the parameter, it will create a plot as we go. And then the last thing is we can print out a table down here that will show us each value. And that's really all there is to a parametric study. Just keep in mind that you're running the study over and over again. So it's good to be somewhat aware of how long it takes to run the study once, and then how many times are you planning to run the study. So in our case, the study computes super quickly, so there's really no concern. But if you were doing something really complicated, you'd want to be more considerate of that. So you just take compute, and then we can click over here, and it will show us our values. cool. So actually, I wanted to select that probe we referenced before. In this case, it seemed to not matter because the default seemed to work out. But just to be clear, the probe that we created is what we'd want to actually look at. So let's just make sure it behaves the same way. And then we can click over here to see it as it's going. So this is a very simple simulation, so it doesn't take too long. But I would recommend, if it takes your simulation longer to run, I would start with bigger steps and kind of do like a bisection method to like make your sweep range smaller before you increase your step size. So once again, what I was hoping to find out is what is the maximum surface temperature that will still be below that 650 C core failure limit. So it looks like it's 616 Celsius. So now we know that if for some reason this exact situation happened again, if we ever got close to 616, it would be time to evacuate. And that's how parametric studies work. So pretty simple overall. And in the next section, I will be discussing how to plot. So a little bit about the plotting features and then how to export your results. Hi, so I'm picking up from the parametric study section, and I'm on step 6. So we'll be focusing on plotting and export from COMSOL. So COMSOL can be really great for producing data, but personally I like to have access to it directly so I can put it into whatever plotting software I want or to do further analysis. So from step 6, I'm going to be showing you how to access some plots that aren't like immediately apparent, and how to export the raw data. So first off, you'll recall from the last problem we wanted to find the hottest surface temperature that was allowable while also keeping the core from 650. So we found that out to be 616 Kelvin. So I'm just going to choose to plot the surface temperature, or the radial temperature profile at 616 Kelvin as the surface temperature. So the first thing is, when you're done with the parametric study, you should turn it off, just so you have less data to sift through, and also so the computation time is lowered. So we have that 616 value. That's really was the goal of it. So we'll come up to parameters and change our surface temperature to 616 Kelvin. So that's what we'll export. So this is kind of like our, what is the temperature profile at the moment of failure? Alrighty, so produces this plot, and you'll notice both from the model we built and just by looking at this that the temperature only really varies with the distance from the center. It's only radially dependent. So we could simplify our data and make it much easier to analyze if we could do a one-dimensional plot. However, with the model wizard, we kind of told COMSOL, hey, I want you to think in 2D, so it doesn't like immediately show the option for a 1D plot. So in order to access this, and I'm on step 2, step 2 of the plotting and export section, we have to right click and select 1D plot group. So this can be used to look at a lower dimension, or this can be used to look at a lower dimension. So we could have done a 2D plot group if we were in 3D, so just keep that in mind to try and think generally. So when we click that, up here it will give us some, up in the top ribbon, it'll give us some common plots. I think a line graph will do just fine for this, so I'll click on it. So what you can do is you can click the define cut line, and this looks like figure 8 in the handout. So what it's going to do is just take the partial along that line of temperature, and we can plot it and just see what happens. So you see we get this parabola where the center of the graph is the center. So that might be useful to you, but personally I think we could just use one radius. We don't need to go across the whole thing. So one way you could achieve that is by moving these vertices. So based on which one of these you click, you'll move a different vertex. So I have this one clicked, which means this one will move. So I just simply put it roughly in the center, left click, and now I plot. And now I have a decent approximation, and this is probably good enough for a lot of applications. However, of course, it's best to be precise. So if we wanted to, because we know the geometry, we know the exact coordinates of things, we should just put those in. So to do that, by making this graph, we created a new identity, the cut line 2D one. So down here. So that is the line we created. So this is the approximation. So me just eyeballing it, these are the coordinates we got. So very, very close to 0, 0 and 0R, but there's no reason to not get it exact. So I'm just going to type 0 and 0 and then R. So now we're going to exactly that point. Of course, we're using meshes, so we're never going to get perfectly accurate, but this is as accurate as we could possibly get, and you can see it here. So now we return to that line graph, and we can pull from it specifically. So in this case, the cut line 2D, and just plot it. And now there wasn't really a visible change because we were pretty close. But that's how to access graphs. So from the results we can get tons of different things, but things fall into plot groups. So just try and think of what data you actually need to show and make it as simple as possible. So we can do some things. So yeah, if your data label is not what you like, that means likely that the data set it's pulling from is mislabeled. So we're pulling from cut line 2D. So if we go into advanced, so the space variable, they're calling it whatever this guy is. So I'm going to change it to radius, and I think that should fix it. If we replot it. Oh, so I have to go back to it. Cut line 2D to R 0, 0, 0 R plot. Oh, data set space variable. There we go. So we're pulling from cut line 2D. It's R now. So that's where we got it from. So if you follow my my directions in the Word document, that will be clear. But what happened is just the data set cut line 2D, if we want to change the label down here, we can use the dataset space parameter, go back up here, and then change it to whatever. So in this case, it's the radius of the rod. So now we've created a graph that I think you would actually want to use, or at least use the data. So now I'm moving on to export. So this is the export data as text section. So it's pretty simple. You just right click on export, and then you have all of these options. So we could just export the raw data, so like have X and Y coordinates and temperatures there, which would be a lot of information. So the utility in setting up the plot in here is we'll get exactly the data we want. So it'll look like that when we put it in Excel. So you would call it whatever you want. So in this case, we're interested in the radial plot. Have to hit refresh. So you change it to whatever the radial plot is that you'd like to use as a line graph, and then we browse and we call it whatever we would like. And it'll appear as a spreadsheet, which means we can load it into MATLAB using the load function, or into Excel by when you look to open the file, you just change the file option to any. There's a little toolbar to the right in Excel, and you'll be able to open it, and then you can process it just how you've always processed things. Yeah, so we can do this with whatever we want. We could do, you know, these guys, and then it will give us X, Y, and then T. Or we can have these isothermal contours. So it all follows the same ideas. So whatever you need, you can plot out this way. And yeah, that's really the main core features of COMSOL. I will show you in other tutorials about how to make more complicated geometries, and then of course just to expose you to more of the physics toolboxes. But really it is pretty intuitive. You determine a conservation equation for a control volume, and then you use boundary conditions to connect it to the outside world or to other control volumes, and you just compute it. And then of course you have to specify things like material properties and initial conditions, but it's pretty straightforward. So I hope this was a good primer. We'll go into some transient work and build off this problem in recitation, but I hope this was a good primer. So yeah, thanks for your time, and thanks for being our pilot class for this. So thank you so much, and take care.